Welcome to Hot Chips 25. Session 1, SoC 1.
Hello? Good. Okay, let's get started. Welcome to Hot Chips. My name is Jan-Willem van der Waard. I'm this year's General Chair. And this year we celebrate our 25th anniversary. We started in 1989, now in 2013 we have 25 years of Hot Chips. And looking back, a lot of things have changed and a lot of things have stayed the same as well. We have seen 25 years of decreasing feature sizes and process technology. For those of you who were here yesterday, we had a flash tutorial. We have multi-level flash cells. This allows us to cram multiple bits in one flash cell. And all of that made it possible that today I can show you. Here it is. USB stick, right? All of you received one. It has the conference proceedings of not just this year, but also the proceedings of all the previous 24 years of Hot Chips. So there's a lot of material on there. It gives you a good historical perspective of what happened in the last 25 years. So if you go back to '89, for example, you will see that that conference, just to illustrate that some things didn't change, was very much centered around the CISC versus RISC debate. One of the presentations was the MIPS RISC architecture, for example. Now, the lines between RISC and CISC may have blurred a little bit. And MIPS may not be the dominant RISC architecture anymore, but companies like Intel and ARM keep the RISC and CISC architectures very much alive. So it's an example of how things didn't really change. So again, take a look at that stick. Wealth of information, I think very interesting. What I noted as well as I went through those presentations of '89 and '90, that a whole lot of people involved in the conference then are still very much involved today. That presentation that I just mentioned was given by John Meshi, and I'm not sure if he's here already, but yesterday he was sitting over there. And I guess if you want to talk about computer architecture in the '80s, talk to him in the break or over during the lunch. Are you here, John? I don't see him now, but he'll show up later, I'm pretty sure. So I've got a few housekeeping announcements. First of all, we're back at Stanford. You will have noticed that. Last year we were in Flint. So you could say it's business as usual, with one exception, and that's the parking. Parking is paved now, which is a good thing. So you don't have to wash your car anymore when you get back from a Hot Chips conference like in previous years. It was a dustbin. Downside is that you actually have to pay for parking. That is us as a conference, not you as an attendee. We rented the whole parking space, but for you to actually use that parking spot, you should put this flyer or a hard copy that you made yourself clearly visible in your car. Stanford wants to make sure that just us uses that parking space rather than people who are just visiting the campus. So that's one thing. The other thing is the Wi-Fi. So there is a Stanford network here, listed here on the slide behind me, and it provides you with access to our Hot Chips webpage. And then if you go to Hot Chips attendees, you will see the proceedings of this year already online. It's password protected, but I've been promised that somewhere, yeah, here. So the password is HSA Flash, and you should see all the conference proceedings of this year online as well. So this should be up to date with the presentations as received, I think, yesterday during the tutorial sessions, right? Some other announcements. Regular speakers, meet your session speaker in the break before your session over here, right? So make sure that he knows that you're here, go through the drill of checking your conference presentation, make sure the microphone is okay and stuff like that. You know how to operate things. For those of you who have questions, make sure you clearly mention your name and affiliation when you do so. Then a note about phones. Use common sense, so either turn them off or put them on mute. Then I would like to thank two groups of people. First of all, our sponsors. They're listed here on the right, or they should be listed here on the right, on the left actually. Especially our platinum sponsors, Intel and Oracle. It's organizations like these who give us basically money, which allows us to keep the cost of this conference down. Now, for most of us, this is a vacation paid by our employer for 2 or 3 days, but we have a lot of students as well, right? So by taking this money, we basically are in a position to keep the attendance fees low. This is a non-profit conference. None of us get paid to do what we do over here. All the money that we receive from the conference sponsors goes basically straight back into your pocket. So thank you for that. Last, I would like to thank the volunteers. During the year, we have a program committee and organizing committee putting this conference together. The days around the conference, we need a lot of help. So we have a group of 15 volunteers helping out. They do a huge amount of work. They've been here the whole Saturday. Tomorrow evening, when you're back home or back in your hotel room, they will still be working here, tearing down the conference. So I'd like to end this introduction with a thank you to the volunteers who help out. And now I'm going to hand you over to Don Newell, who's the co-chair of the program committee, and he's going to tell you a little bit more about the contents of the program. Don? Oh, sorry. I have one more thing. There is a red Toyota in the parking lot with the license plate 4517427, and the lights are on. Right? So, if it's yours, go fix it.
At least they didn't email that message to all of us. So, hi, welcome to Hot Chips 25. He actually just covered most of the relevant material in terms of administrative overview. I do encourage you to take a look at the archives from the first 24 years. As was described, you can get a sense of what's happening today by reading through the older material. Relevant to that, I think around Hot Chips 10, we had a presentation on IP as it relates to semiconductor technologies. And again, we're going to have such a presentation today, more relevant than ever before, I suspect. So don't miss that one. Want to also say a few words about the way the conference is going to take place. So we're going to have breaks outside on the patio where you came in this morning. The reception this evening will be held across the street. So don't miss that if you have time to spend after the conference is over this evening. I'm also going to bring up on stage Alan Smith, who will give a brief memoriam to an individual who had contributed quite a bit to Hot Chips over the last years. He was influential in bringing papers from overseas and getting them represented here at Hot Chips, which has been invaluable. With that, I would like to bring Alan Smith up to briefly discuss Mitsuo Sato's contributions.
I just wanted to give a very, very brief memorial for Mitsuo Sato, who's been a major contributor to Hot Chips over the last 20 years. He's been on the program committee, I think I counted 13 times. I've worked with him at Toshiba. He's a great guy. He was chief fellow at Toshiba. Prior to that, for about a dozen years, he was general manager of the semiconductor division. And he was unusual in that he understood computer architecture. He knew what worked and what didn't. Worked on a number of projects, MIPS processors, Spark processors, cell engine. Wonderful fellow, good at mentoring young engineers. For any contributor from Japan, he had something that was very important, which he spoke good English. So we were able to communicate well. very helpful. Also, as an executive, he was able to use travel budget to get over here and attend the conference and attend some of the program committee meetings. And he died at the end of March. Unfortunately, before our program committee meeting, a sudden stroke. And apparently, he was taken ill at his retirement party, which is rather sad. Anyway, we'll miss him, and hopefully we'll find somebody well qualified, although it's hard to find anyone who's well qualified to serve on the program committee from Japan, but we'll start looking. We also have a second very brief memorial of Kim Il-soo, who is another long-term participant in Hot Chips. He was on the program committee once, was registration chair several years, and Bin Chuang from Broadcom, who's a colleague of his, will again make a very short presentation.
Hi, my name is Bin Chuang. I met Kim 20 years ago at IBM Austin. At that time, he was the research from Yorktown. He do a lot of research for computer architecture and CAS. 10 years later, we met again at Broadcom, and there we work again. Kim was the architect for our embedded processor that go to many of our SoC. As Kim, he's a great mentor, and he's a great engineer that very advocated to work to make sure we have the best design for the low cost. As a friend, he's always been great to everyone around him, and he always very inclusive. So at Broadcom, we miss him very much. He worked to the very last day. He passed away last year of cancer after a year and a half or so with fighting with it. So we all miss him, and thank you.
Okay, with that, let's start the technical program. The session chair for the first set of papers, the SoC papers, is Benham Robotomili from Qualcomm. I'll have him come up and introduce the speakers now.
So for the first session, we have 3 presentations on SoC, or System on a Chips. We have presentations from AMD, Microsoft, and Intel. So the first talk is on AMD's Kabini APU SoC. The speaker is Dan Bouvier. He's an AMD Senior Technical Fellow and Client Product Portfolio Architect. Dan leads the architectural definition of all AMD's tablet, notebook, and desktop APUs. Prior to joining AMD in 2009, he was processor CTO for Applied Micron. And before that, Dan spent 9 years at Freescale, where he was the director of advanced processor architecture and led the definition of high-performance PowerPC processors and PowerQuick SoCs. He was also the principal architect of Rapid I/O interconnect architecture in 1999. Dan has a bachelor in electrical engineering from Arizona State University and holds 17 patents. So let's welcome Dan.
All right, thank you. Well, I'm glad to be here to talk about a chip that we're very excited about called Kabini. Kabini is actually a small, well, actually for small in certain respects in that country, but as a river in southern India. I actually named this chip early on when I joined AMD it's a tributary river to Kaveri, and as you know, we're anticipating another chip coming up. Maybe we'll be talking about that next year called Kaveri. Anyway, so we'll get into it here. So I figured I'd start kind of the opposite end of the way a lot of these talks go, and I'd go straight to the sand that makes up Kabini. And so the floor plan. So this is a 28 nanometer device. It's a 105 square millimeters, and we're just shy of 1 billion transistors in it. This is considered in our realm one of our targeted low power devices, and it's just phenomenal to me to think that we're at 1 billion transistors in such devices. And interestingly enough, there was not enough to do everything we wanted to do. It seems like there never is. So I'll walk around the floor plan a bit here. So first of all, we're introducing in this device our Jaguar x86 cores. And we jumped from our previous generation part called Ontario, which used our Bobcat family or Bobcat core, to Jaguar. And we moved from a dual core to a quad core in this device. And so this is a very significant move in terms of performance, especially in the power envelope we're working in. We also integrate all of the system I/O, of course, a very high performance memory subsystem. We have integrated graphics. This is an APU, or an accelerated processing unit, so it is a complete system on a chip. We have a display engine, and as well as we're still carrying VGA, maybe for another generation or so. And then we have all the system connectivity on the device. So, and one of the things that struck me is, as I was working this, we were talking about how these chips have changed over the years. We used to focus on the CPU, I remember years ago at this conference, and how good was our branch predictor, and how good did we get the load store to work out. And it's funny how things have shifted to where we're now talking about these complex SoCs with all sorts of systems and processors. And what doesn't show here is we talk about the 4 cores, but there's several micros on this device in the GPU, running power management, even in the DRAM interface. What is also interesting is the number of folks that were involved in putting this together, and that is just a management challenge in itself. CPU cores were done in Austin. The graphics was done in Orlando and in our shop in Markham, and as well as the accelerators. PCI Express PHYs and DRAM PHYs done in Boston, and Northbridge done in Sunnyvale. Southbridge and System I/O done in Shanghai, and then the complete SoC was done in our team in Hyderabad, India. So an amazing, amount of people to coordinate to pull something off like this. So we'll kind of work through, and I'll start with Jaguar Core, which we presented at last year's Hot Chips. So Jaguar had 3 basic tenets that were behind putting it together. First of all was to improve on the Bobcat core, really both in IPC as well as better or higher frequency per volt. In other words, giving us more performance per watt. We also needed to do some updates in the ISA, and I'll talk through a couple of those items in a minute. And then last but not least was we wanted to set up the processor to have better process portability, to give us more flexibility as to where we put the end device, and so that was another key in the device. The Jaguar enhancements that we did, kind of working from the top, is first we improved the instruction cache prefetcher and put a larger instruction buffer. We added some new hardware around the divider and improved the complex operations quite a bit, and added some new instructions as well. We added more out-of-order resources as well into the processor. In the load store, we did a complete redesign of the queuing to improve the efficiency there with the complete memory system, and then in the bus unit, we also improved the number of amount of write combining and more outstanding transactions. So then we took that core and we changed the cache of the L2 subsystem, and we built this in a cluster. And so it's physically built around a cluster that shares a shared L2. This is a 2 megabyte L2 with 16-way set. It is an inclusive cache, which is very nice for dealing with probe overhead from outside peripherals. And it also runs at the core clock, so it's a very high performance L2. This sits on top of our unified Northbridge, or as we call it, UNB. Our UNB is includes basically the coherence domain. This is where the microprocessor intersects with the I/O subsystem and the memory system. And so in this, we'll have our system request interface and then a crossbar to connect our high-performance I/O, graphics engine, and so on through to the memory system. Then also included is our DRAM controller. The DRAM controller in this device is a DDR3 single channel, as we call it, a 64-bit interface. It runs up to 1600 megatransfers per second. And interestingly, it does support up to 2 DIMMs, 4 ranks, which is interesting because in this device we're covering from tablet all the way to desktop, so that meant that we needed a good amount of memory span as well in the device. And that all sits, by the way, in what we call our FT3 BGA, which is the primary BGA device this lives in. The I/O subsystem connects in to this through an internal interconnect, and our I/O actually are logical PCI devices. So the device to software looks like it has PCI peripherals on it. Next, I'll talk about the graphics on the device. So the graphics, we're using our graphics core Next architecture, and this was a major revamp or redesign of the Radeon family of graphics controllers that was announced and put into the market just over about 1.5 years ago. This is the first APU to integrate that graphics core Next architecture, and we're very excited about this. The main tenet behind the graphics engine was to move away from being a pure graphics engine and allow it to be a true GPU and bring all of the necessary components to do computation as well as graphic scene rendering on it. So this meant that we added a change in instruction set. We built this much more for power efficiency and also sets us up for heterogeneous computing. So this is, as I mentioned, the first generation. This is our 8000 series graphics. So it's really the second generation of the graphics core Next. And so this supports full DirectX 11.1, gives us great 3D performance, OpenCL.1.2, and all the other good things that come with latest and greatest graphics. This device has 2 graphics compute units, and so on the next slide I'll talk about what that does. And then has 1 render backend in the graphics engine. We did spend a fair bit of time on power management, doing some fine-grained power gating in the graphics engine so that we can adjust on the fly the amount of power based on the workload. So the building block in the graphics engine is our CU, or compute unit. The compute unit is made up of, as we call them, 4 quads, and those are SIMD engines. They're 16 wide, or 4 quads, as we call them, SIMDs. Each one of those SIMDs can be scheduled independently. So as I mentioned, I have 2 compute units. I've got 4 quads in each, 4 quad pipes in each one, and those can all be scheduled independently with different wavefronts moving through. This gives us a very high performance. Our peak, especially for a class of device of this class, we're doing just shy of about 400 gigaflops of throughput in the GPU, which to me is a phenomenal amount of floating point performance in a device that goes in a tablet, potentially. So this is with the architecture change. This became we moved off our VLIW architecture, moved into a more classical instruction dispatch architecture, and this again helps to improve the programmability and ability to adapt to not only graphics workloads but also computation workloads. The graphics engine also has a cache subsystem. Graphics engines are starting to look more and more like regular old CPUs that we know and love. This does have an L1 cache on each compute unit, and then it has an L2 texture cache as well. And those caches are kept coherent with each other and do support other things like global atomics in the L2. There are three other acceleration elements associated with the GPU. The first is the display engines, and so that we have two display engines on this device. The display engines do all the post-processing for setting up the visual experience, and it's a piece of IP that we're very proud of. Our display engines support both HDMI and DisplayPort, and then we also have a VGA DAC, as I mentioned earlier. So we can support EDP for a display, or we can support external HDMI or even combo HDMI or DisplayPort. The video codec engine is an encoding engine. It's a dedicated accelerator. This allows us to do encode of like H.264, for example. And then we have our UVD, our universal video decoder, and this does decode. So the combination of those two can do a full transcode for various applications, ripping and so on. To talk a little more about our display technology leadership, so first of all, the device does support up to 4K displays, as we're starting to see those show up in panels, not necessarily in the device itself, but TVs and so on to plug into. We also have a very impressive Wi-Fi display. We have the ability to support the Wi-Fi certified Miracast standard. We have an extremely low latency. We have a direct path between our video codec engine and our display engine. So we can go from display of the scene straight to our video compression engine, straight to memory, and then out through Wi-Fi. This makes it, if you ever get a chance to see a demo or happen to get one of them, very usable for even gaming and so on. There's no lag between the control and what shows up on the panel. We also support panel self-refresh and dynamic refresh rate in panels, and those are if those panels do support that technology, so again for low power. The whole subsystem's tied together with a series of interconnects. So at the top level in this picture, what I'm showing is our Fusion control link. This is a path between our I/O subsystem and the North Bridge, and this is our coherent path. So most traffic that's coming from PCI or our control traffic to our graphics engine follows through that path. But in addition, we also have a high-performance path that goes directly from the graphics engine to the DRAM controller. It actually bypasses the North Bridge and goes right to the DRAM controller. So this allows us to have a very high-performance path from the graphics engine, and the graphics engine actually has a highly choreographed DRAM control engine or memory controller in it that we call our GMC. We also have an integrated system control and I/O hub where we have all of our high-speed and low-speed interconnects to make it a complete SoC. And the next slide shows how this all comes together. So we have all the necessary system interconnect on the chip. We have a clock generator, and interestingly enough, the device also has a discrete PCI bus for discrete graphics. And so in some applications, especially desktop, we see devices like this attaching to a Radeon discrete graphics controller. So one of the areas that we did spend a fair bit of time, as I'll show you in the next few slides, is in the power management of the device. And so power management is interesting because as we analyze the workloads and have now for a couple of generations of APUs, we find that that power and work shifts on the chip very dynamically. And so workloads are not all created equal. We'll have some that are very computation or CPU intensive, some that are graphics, some that are I/O, and the mix. And so we needed to set up the architecture so we could move that power around. We also took this into account in the floor plan, and I'll show you that in a minute. So we have monitors in the CPUs where we monitor their switching activity, their CAC, and we also monitor the same with our GPU, with our I/O subsystem, and with display. All of that goes into a controller that we have, a micro on the device, that then runs algorithms to figure out when the best time is to move power and adjusts the power management states of the device. So this is an example of some of the analysis that we did. And as you can see, this is a graphics-centric, and this is a real workload that we grabbed the power calculation out of. And what we find is that in this case, most of the energy in the chip is going to the graphics engine and very light load to the CPUs. We actually floor planned the device to take advantage of this and to sink power or heat thermal to, in this case, the CPU can act as a heat sink. If I look at the opposite end, when I have a CPU-centric workload, here you see the GPU acts as a heat sink for the CPUs. And so we exploit this in the algorithm and then move power back and forth depending on the situation. So what does this mean? It means that the performance per watt, we made a significant increase from our previous last year's chip, the Ontario device, on the order of about a 200+% improvement in performance per watt in 3D Mark 11 and about 170% improvement in PC Mark 7. So the contribution of the technology shrink from 40 nanometer to 28 and the power management and then adding more computation onto the device contributed to this increase in performance per watt. And what that's doing is giving us notebook class performance in a very low power envelope. And then the other aspect, I've got some various scores here, some scores that as you can see, this is a real PC chip, not a low performance tablet. It will give you a full user experience, but it does it with great battery life. And so while we're seeing great performance scores, we're also seeing very good extended battery life. Here with a 33 watt-hour battery, we're talking about greater than 9 hours of idle time and about 7 or 8 hours of web surfing time and so on. So very usable and not having to run to plug your computer into power strips like we have here. It should last the whole day. The other thing here is the system power and the aspect that we're controlling there. We saw, as I mentioned, about a 25% improvement in overall power efficiency moving from our Ontario device to the Kabini platform. Then we have the notion of generational performance per watt improvement over our mainstream products. And so what I have here is a picture of our Trinity device from last year. We'll be talking later about our newer version, Richland, but this is compared to our previous generation. And again, you can see the incredible performance per watt improvement that we made there compared to both Trinity and the Trinity device. So very good improvements there as well. And again, this is the first x86 quad-core, full-up quad-core that we're seeing into the entry space of the market. So really, in summary, we've, as I've pointed out, we've got more cores in the device. We've gone to a full-up quad-core. So this gives us a great user experience and the ability to use this processor in a full PC experience. We have better graphics, moving to our Core Next, Graphics Core Next architecture. And then we have the ability to do all-day computing with the device. And so giving more than 10 plus hours of user experience. So just to show that a lot of people don't know that AMD is living in tablets and some pretty impressive tablets, I brought along an 11.5-inch tablet that we're pretty proud of. This is a ODM model. There are actually models on the market today that you can buy that look similar to this. It is a full 1080p display, beautiful display on this, great viewing angle too, and has the ability to run with a full game experience. For example, I'm showing Torchlight 2 here running in a loop. But again, it gives a great user experience in a 1080p display with great battery life. And so really nice size screen to work from. So with that, thank you. And I guess we can take some questions.
I'm Todd Besnick. I'm self-employed. The power monitoring capabilities, are you exposing those external to AMD?
No, it is a pretty tight control feedback loop that we have, and it is a closed micro. What we do, though, is we tend to work with OEMs, and we do sometimes do tuning to the specific thermal design, and so those aspects we have done.
So this can be very useful. Like there's a poster outside right now from UC Santa Cruz, I believe. Somebody built a power emulation tool for simulator. And things like this can be really great for validating this stuff because we know it's really hard to...
Yeah, great to take a look at that. Good advertisement. Question over here?
Dominic Schmidt from QVT Capital. Are you using the same metallization scheme, the metal architecture as you did with Bobcat with metal 1 through 8 on match metal pitch? Yeah,
very similar stack. The design was set up to go into a more classic bulk process technology and metal stack scheme. Yeah, absolutely.
Israel Cohen from the University of Massachusetts. It's sort of a follow-up to the first question. What triggers the power management? Is it temperature or it's a fixed frequency?
Yeah, great question. So our power management, one thing I declined to mention is that we also have thermal monitors on the device. So we have probably a dozen thermal sense devices, and then we also are managing based on the activity that's going on. And the activity is a hand-in-hand shake with the OS, so we can see in handshake with the standard APM that you'd have with Windows in this case. Then you move down a layer, and we manage based on what we're seeing in activity in the CPUs. Since we're dispatching through our driver to through a microcontroller to our GPU, we can monitor what's going on workload there, and basically then we set based on the activity and calculating, as we call them, thermal credits. But then we're in the background monitoring the thermal sense points to make any adjustments into that feedback. So the very tight loop is done based on thermal credits that we're calculating based on switching activity, and then longer thermal excursion events we're watching through the temperature monitors.
But if the OS is involved, what's the smallest interval at which you can make power management changes?
Oh, we're making power management changes on microsecond and possibly even finer depending on what it is. But yeah, obviously if the OS is involved, that's a much longer tick interval where we'd be getting hints to make changes at that stage. Okay, I think that's the last question. All right, thank you.
Thank you so much, Dan. We are a little bit ahead of our schedule. And okay, so the next talk is about Xbox One. It actually has two parts, and two speakers are going to present this presentation. The first speaker is John Sell, is going to talk about main SoC of Xbox One. John is a hardware architect at Microsoft who is involved in CPU, GPU, fabric, and SoC design. Prior to joining Microsoft, he has been a senior fellow at AMD, CTO of 3DO Company, and before that, he was a distinguished engineer at Apple. He has a master in electrical engineering and computer science from Berkeley and bachelor from Harvey Mudd College. The second part of the talk is going to be presented by Patrick O'Connor. It's going to be focused on Kinect sensors for Xbox One. Patrick is a senior director of engineering at Microsoft and is responsible for hardware and software development of sensors and custom silicon in Microsoft's natural user interface platforms, such as Kinect. Prior to joining Microsoft, Patrick was VP of engineering at Canesta, and before that, he held engineering degrees at Parthus Technologies, Oriel Semiconductor, and Analog Devices. He holds a bachelor in electrical engineering from Dublin Institute of Technology and University of Dublin Trinity College. So just a side note, well, there's lots of interesting questions regarding marketing and business related to Xbox One release. Given that this is a technical conference and a technical presentation, please do your best to focus your questions to the technical aspect of the presentation. Thank you.
Thank you. A couple minutes here. So this is the Xbox One. And Patrick and I are going to talk about the main SoC and the Xbox One Kinect today that are shown in green. But to put those in the system context first, there's also a new game controller, the orange box. It's wireless. And inside the system, there we have a custom South bridge that integrates I/O, clocks, most of the other common system management functions. We have 8 gigabytes of DRAM, a 500 gigabyte hard disk, 8 gigabytes of flash storage, and a Blu-ray drive. The main SoC was developed by us in conjunction with AMD, and it's one of the largest consumer designs to date. It's 363 square millimeters in a 28 nanometer process. That's the net size of the die. It's actually 381, I think, with the scribe. Has approximately 5 billion transistors. About half of those are used for the rather substantial about 47 megabytes of cache and other on-die storage, and I'm going to talk quite a bit more about that storage in a couple minutes. We use a very large number of power islands and extensive clock gating, power management, and lowered voltages and other techniques to allow this large SoC, though very high performance, to also operate in modes down to less than 2.5% of its full performance, full power operation. Inside the SoC, the principal components, besides, of course, the CPU and GPU, are 15 other processors that very substantially offload those. My GPU colleagues get mad at me when I put the GPU in a little tidy box, the one down in the lower left corner, but it does represent, this drawing is not to scale. One of the most important aspects of the design is that all of the components, when they access memory, they do so through nested host-guest MMUs. And this allows us to do a number of things, but probably the most important is we have a seamless sharing of memory between the CPU and GPU and the other processors. And so when processing moves between on a given piece of data between the CPU and GPU and back again, they can just pass pointers. Those of you that were at the tutorial yesterday have heard a good deal of discussion of these kinds of techniques. When the other thing which using the two-dimensional MMUs allows us to do is to let applications and system services that we provide to essentially get very close to the metal, so we can let developers have access to very direct programming of the GPU without a lot of overhead. The memory system consists of the 8 gigabytes of DRAM and also the 32 megabytes of on-die storage. And the best way to think of this is essentially 8 memory controllers. for the actual physical memory, 4 of them for the DRAM, 4 for the on-die storage. The DRAM are 4 by 64 bits. The on-die storage are 4 by 256 bits. Data structures can be scattered between them on a page basis, either 4 kilobytes or the larger sized pages that the x86 architecture supports. It's based, of course, on an address, which one, physical address, where the accesses are actually directed. The memory system is designed to meet the performance requirements, which are very substantial, and do so with the lowest cost and especially the lowest power. With the majority of memory access being directed at the on-die storage, it's a very substantial power savings versus going off chip. The total sort of typically realizable bandwidth is something over 200 gigabytes per second. The peak bandwidth for the DRAM is 68 gigabytes per second. The peak bandwidth for the on-die storage is over 200 gigabytes per second. It ranges from a minimum, depending on the mix of transactions, of 109 gigabytes up to 204. Another key aspect of the design is we wanted to let any of the DRAM data be coherent with CPU caches, and that is the case. There is that isn't free, though, and so we've provided 2 paths to DRAM, and those are illustrated in the kind of light blue arrows and then the sort of greenish yellow arrows. And so there are 2 ways to get to the DRAM controllers, and page tables indicate on a page basis whether a page is coherent with CPU caches or not. Next slide is shows the structure of the CPU. The CPU consists of 8 AMD Jaguar x86 64-bit cores. I'm not going to talk too much about what's inside the cores, as the previous speaker mentioned. AMD did indeed present the details of Jaguar at Hot Chips last year. Each of the clusters of 4 cores has a 2 megabyte L2 cache. And the one thing that is unique about the implementation in the Xbox One is we've made some alterations to the CPU clusters to support the high coherent bandwidth, both between the clusters and also from the GPU and other processors that I mentioned a second ago. Focusing on the GPU, it's we call it it's a DirectX 11.1 GPU. We call it a DX11 1 Plus, and the Plus refers to some unique features for Xbox One. Probably the most important of these are the control processors. There are 4 custom graphics and compute command processors. These have been customized to significantly reduce the amount of time, the amount of work that the CPU has to spend in assembling graphics commands. They've also been altered so that they do support the shared memory with the CPU that I was describing a couple minutes ago. As I mentioned, there are 15 significant processors that are offloading the CPU and GPU. One set of those shares the GPU MMU, and those are the green boxes across the bottom of the diagram. They include a engine that resizes and composites up to 3 surfaces. Prepares those for video display and can also copy them back to main memory for replay and various other purposes. There are 4 copy engines that can also compress and decompress textures and other data in various formats. And they can transform the tiled formats that the GPU uses into to normal linear data formats, or back again. And then there are video encoder and decoder engines that support basically a full range of standard formats. The other main set of processors, of special processors that we've added, are the set of audio processors. There's actually, let's see, 1, 2, 4, 5, 6 of 8. I'm not counting the DMA engine. These are designed completely by Microsoft. They offload the CPU especially, and they represent more than a CPU core's worth of processing. Of course, they're much smaller and lower power than if we were using general CPU cores. They also have multiple work queues like the GPU and use a host guest MMU, and that lets them also be shared by system services and by the application. The Kinect system that Patrick's going to talk about in a minute uses them extensively for its directional audio capture capabilities. So to conclude or summarize the SoC part of our talk, it really gives probably the most important points that I want to leave you with is we have tried to design the system so it balances the significant bandwidth requirements with delivering a cost-effective and power-efficient design. Also that, an important aspect of doing that is letting the CPU and GPU share memory spaces and work efficiently together. And some of the other key points are that the system is designed to work as a media hub with HDMI in and out, and includes all of the various other special processors that help make it an overall very high performance and cost-effective package. So with that, I'm going to turn the podium over to my colleague to talk about the new Kinect for the Xbox One. There we go.
All right, thanks, John. Thank you. Good morning. So I'm going to talk a little bit about the Kinect. We wanted to produce a Kinect that had a true next-generation performance. So the new Kinect system includes a full HD 1080p color camera that has been substantially optimized for operation in low light conditions, so that in a normal living room environment we can get great video for experiences like Skype. It also has the 4-channel directional microphone for beamforming to get the best possible audio quality and voice recognition capability. But in my talk this morning, I'm going to focus on the depth sensor, which we developed to greatly improve and bring to a new level the user experience that you get by moving around, using gestures, etc., for interacting in a natural way with the system. So what goes into making a next generation experience for Kinect? First of all, we wanted to ensure that we get very consistent performance across all people that are using the system, whether it's small kids, large adults, and maybe more challenging when both of those are playing together or sitting together in a room. And so you need a system that can see, large people close to the camera, small people far away from the camera, both interacting at the same time. And what that comes down to, a child's wrist is of the order of a couple of centimeters.
And so in software, being able to identify and track objects that small, even when it's 3-4 meters away from the camera. Place-based flexibility. We wanted it to be able to work in small rooms, to be able to work in large rooms, to be somewhat independent of the user's situation, so that the system is robust and everybody using it gets a great experience. And we can rattle off the numbers, but we want to be able to operate very close, maybe less than a meter, 0.8, 0.5 of a meter from the camera. Wanted to be able to operate out to 4.2 meters for larger play spaces. This translates into a 70-degree horizontal field of view, or almost 90-degree diagonal field of view. And in general, the system needs to be accurate, responsive, and consistent for different players and different times. So this translates into a high accuracy in measuring distance, low latency for a very responsive system. You make an action, the system responds straight away. So of the order of 20 milliseconds from when the sensor detects it to when that result is delivered to software. And very short exposure time, which translates into motion blur. Someone is moving quickly, you don't want to lose that motion. You want to track that motion and enable lively gameplay and make it a fun experience. And finally, lighting independence, just being able to operate in any living room. Some people like to watch movies or play games in low light conditions. Others have bright sunlight coming in the window, etc. That shouldn't interfere with the performance of the system. So in order to cover this pretty challenging list, we at Microsoft have designed a new 3D depth sensor based on what's called time-of-flight technology. And this is where we use the speed of light as a property that enables us to measure distance. And I'll talk a little bit about that. So the core of this new sensor is a very specialized pixel. It's a differential pixel. And if you think of a camera system that has an image sensor like a regular camera with this specialized pixel array, but there's a timing generator in the camera, and the timing generator clocks the pixel. It also clocks the light source, and there's an external light source like a flash, except it's being modulated. And so we illuminate the room with this modulated light. And we generate waveforms like this. So we put out a light signal that looks like a square wave, modulating it in the 10 megahertz range. It goes out from the camera, bounces off the object, say my face or whatever it might be that we're looking at, and returns to the camera. And the sensor sees an incoming modulated waveform that's out of phase with the waveform it sent out. And that phase difference gives us everything we need to know about the distance the light has traveled. So by knowing the modulation frequency, we can calculate the time it took for the light to travel. And by knowing the time, we can calculate the distance. Light travels a centimeter in about 33 picoseconds. So the good news is that in CMOS, we know how to manage timing. We know how to manage frequency. These are well understood in the industry. And so we were able to construct a system to do this. And the key is this differential pixel. The core of the pixel is that we have a clock into the pixel. And the pixel has two outputs. When the clock is high, any charge that's generated within the pixel when light hits it is swept to the A output. And when the clock is low, any charge that's generated gets swept to the B output. So by looking at the difference of A and B, you get some information about the time of arrival of the incoming light. And in fact, it enables you to calculate the phase. If you think of a phase discriminator, people familiar with FM or any of these basic systems, if you can measure with a local oscillator, you can measure an in phase and a quadrature component, then you can estimate the phase of the incoming signal. And just exactly the same way, our timing generator allows us to rotate the phase of the clock going to the pixel. And so we can detect the incoming phase by taking a few shots at different phases. So at the bottom of the graphs here, you can see, as the clock is high, you see the A output integrating the charge that's coming in. When the clock is low, the B output is integrating. A plus B, if you take those two outputs and just sum them, you get a result that's kind of independent of timing. So any light in the room, like room lights, will show up in A plus B. But if you take A minus B, any standard lighting like this is actually canceled out. So it has this wonderful property that you get an output which is actually independent to first order of any room lighting, sunlight, anything like that. So it gives us a very rich output. We can estimate ambient lighting in the room by looking at A plus B. With A minus B and an arctangent function, we can figure out distance and get a three-dimensional view of the objects in front of us. And then by taking the magnitude of A minus B, we get think of it as a grayscale image that's completely independent of room lighting and is only dependent on our own generated light. So the nice thing about this system is that you get resolution in the XY dimension just by the number of pixels you put in the array and the quality of your lens. You get resolution in depth by the electrical parameters, such as how much current you drive in your light source and your timing control in the system. And then overall signal to noise ratio, which is governed by light and by optics and so on. So it's set up by electrical and optical parameters, no fine mechanical tolerances, nothing like that. So once you figure out the CMOS, you can build it in high volume and have a very robust product. So you end up with something like this. On the top right is our sensor chip. It kind of looks like a classic image sensor, a large pixel array. In this case, the output from the pixel array is differential, and the A to Ds and the data processing is all done in a very differential manner, fully differential signal paths to maintain this A minus B property as accurately as possible. The timing generator, which is unusual in an image sensor. And of course, the timing generator runs clocks through the arrays, meaning that the power consumption of the chip will be higher than a normal standard static image sensor. And then that clock generator drives a signal out, which drives an external light source driver. And so we can build a system that has the sensor, a light source driver, then a light like a laser LED, and a returning sensor lens. And at the bottom there, there's a small SoC in the camera that we designed as well. This is mainly just a data consolidator. So it talks to the depth sensor, talks to the RGB color sensor, talks to the audio acquisition A to Ds, and then packetizes and sends it all to the host. Some of the challenges we had along the way. I talked a little bit about being able to detect multiple people in the room at the same time. So we need to maintain a minimum signal-to-noise ratio just to get the depth accuracy that we require and the noise level that we require. But this has to be done for multiple players. We want to be able to support up to 6 players all interacting continuously at the same time. So that's a challenge. As you move away from the camera, the brightness of the light falls off with the distance squared. So for someone very close to the camera, they're going to be very bright. Someone 4 meters away from the camera, it drops off by a dramatic amount. Similarly, reflectivity of clothes. We're covering reflectivities of the order of 95% all the way down to 10 or even lower. So this sets up a high dynamic range requirement. Normal photography, you can play with aperture, you can play with shutter time, but because we've got different people all interacting at the same time, we can't do that. We always have to be able to see the darkest person. We always have to be able to see the brightest person. So we end up with a dynamic range requirement of the order of 2,500. So to cover this and to make it work, in the image sensor, we can take multiple images at different points during the integration, during the image capture. And at each pixel, dynamically, we can choose which result to use. And so you end up with a very high dynamic range image because every pixel is selecting its own shutter time in real time. Another issue, I mentioned that the system basically measures phase. By knowing the modulation frequency, we convert that to time and so to distance. The higher the frequency you use, the finer resolution you get, because think of it as a yardstick. Your 360 degrees get mapped to a finer and finer time as you raise frequency. So you get higher resolution, which is good. But at 360 degrees, phase wraps around. So in this chart, you see phase on the vertical, and distance on the horizontal. What happens when phase wraps around? Well, we get ambiguity. So we get a measurement, and we're not quite sure which ambiguous range it's going to fall into. So one solution is to drop the frequency, but you lose so much resolution by doing that. So instead, we use a second high frequency, so we maintain our nice fine resolution. But by correlating the results of these two outputs, or more, in fact, you can get a very robust long-distance measurement at high frequency. And this means we might more or less get our cake and eat it. Room lighting conditions. I mentioned that a little bit. I'll just give you an example. This is a picture I just took with a cell phone camera. It's not taken from our own camera. But it just gives you an idea of the kind of challenge software has to deal with. You get an image that's side-lit. It's very difficult to pick out the face. So giving a very, very nice, consistent recognition or detecting what the face is doing in those conditions is very, very difficult. This is the image from our active system, where we reject ambient light and just see it as lit by our front-facing camera light. Beautiful software, love it, and it works very well. We're going to give you a little video. It's a very amateur video made by some of the engineers, so don't expect a nice Microsoft presentation here. But it'll give you an idea of what depth looks like. This is real time, no averaging, 30 frames per second. Hopefully you can see. Okay. Yeah, just two people moving around. You'll see fine features. You'll see facial features. You'll see fingers and hands. And as they move faster and faster, you'll see that we're able to track this motion in real time because of low exposure time and high frame rate. This is what Microsoft engineers do in their spare time. Okay, that's it. Thank you very much. Do we have time for some questions?
Okay.
Good morning, Rick Merritt from EE Times. Great presentation, thank you. Video game consoles have a long history of custom development with partners. I wonder if you could talk a little bit about the heritage of some of the aspects that you might be using in the partnerships here. For instance, the GPU, was that based on a Radeon? And the time-of-flight sensor, was that based on some other partner's technology? And then the process that it's all built in, is that standard TSMC 28 or something unique? So partnerships along those three lines. Thank you.
Well, I'll start with the SoC parts of that. The SoC is built in a 28 nanometer TSMC HP process. It's a standard process. As I mentioned in my talk, it was developed in collaboration with AMD, and almost every aspect of it, however, has been customized either a little or in some cases a lot for the Xbox One implementation.
Yeah, in the case of the depth sensor, the technology is homegrown, so it's all internal Microsoft development. We do work with TSMC for the fabrication and other partners for the manufacturing, but the design and the core technology was all developed in-house.
The GPU, as I mentioned, its heritage is AMD, and actually in the Xbox 360, it was of course an ATI GPU. But beyond that, it has been customized in various ways for the Xbox One, and that's all that I'm going to comment on at this point.
I'm kind of curious about the coherent interconnect between the two quad-core clusters and the nature of that. Is that some flavor of hypertransport? What's the bandwidth, and how are you handling the snoop traffic between them and hopefully minimizing it?
Well, the coherency connections are a derivative of AMD's hypertransport. What's unique about the Xbox One implementation is the bandwidth, which is that we can sustain about 30 gigabytes per second of coherent bandwidth, is increased, and that is involved in increasing queue depths and providing appropriate pipelining and width and bandwidth of the interconnect.
And do you have any like inter-cluster Snoop filtering? Oh, sorry.
Yeah. The answer is no. We're not filter. We don't have a Snoop filter. We considered having one, but just based on the bandwidth which we're able to sustain, the cost, schedule, all those kinds of issues, decided that the best combination was to not do so in this particular design.
Okay. Todd Besnick again. So now, John, we know what you do when you're not helping out with hot chips all the time.
Yeah, well, fortunately, hot chips is only 3 days a year, but I get more physical exercise here.
So is there anything remarkable that you'd like to pass along in regard to the on-die RAM cell design that you used?
Well, it's there's nothing. The actual bit cell is the same. There's actually just one bit cell that's used for all of the memory. As you might imagine, different sized memories have different detailed structure in terms of the arrays. One of the nice things about the on-die memory, however, is, as I mentioned in the presentation, it's much lower power. The die itself, of course, it does make it contribute to the large size of the die. However, the memory is repairable, as you'd imagine any such large structure would be. And that means that, it adds to it reduces it defines the number of chips that fit per wafer, but it doesn't have a very large impact on the yield.
Hi, Mike Wan. For a quick question, as a developer for your first Xbox Kinect, I'm really happy that you guys cut down the latency from the camera to the system. I was wondering, did you mention how many frames per second your sensor is capable of, like an actual number?
Yeah, it's running at 30 frames per second.
And is your data, the packet that you send over to, can you configure it to say only send RGB or only send depth images, or does it just give you the whole load?
It gives you everything. So yeah, the data is sent, like depth and color and audio are all interleaved. But as far as the system is concerned, it receives a packet of these every 33 milliseconds. And it's all in memory. So DMA takes care of a lot of it, very little overhead. The latency is key, as you know, for any kind of user interface. And we measure latency. I'm a hardware guy, so we measure latency from the first photon hitting the sensor, so the first time you begin to see what the user is doing, to the first packet delivered into CPU memory. So from when we get it to when software can start working on it. Then, of course, there's additional latency for the actual software implementation.
Morning, Michaela Blood-Silings. Given the enormous die size, do you consider stacking for next generations?
Are you thinking of stacking of memory, or?
Potentially, yeah. You have a considerable amount of memory on chip.
Mm-hmm. Well, there are various options that we will consider, as we will most likely be cost reductions like there have in the past. But it is true that because the memory is repairable, it doesn't really contribute negatively to the yield of the die, and that's the most important cost factor. So it's not really we obviously like to make things as small and cost effective as possible. So we'll look at it. We'll always be looking at such techniques, but it's not really a major concern. I think meeting balancing the performance requirements that we had and power and so forth were more important concerns.
Hey, Chen Li from Samsung. I got a question about the acoustic system, acoustic sensors and the microphones. Like, besides using them for the recording audios, are those like sensors used for like positions or other purposes?
Not really. The depth sensor does all the positional detection. It's actually the other way around. So the 3D system can figure out where people are, and that can help the beam steering algorithms to focus the audio quality, let's say, to the speaker or to the individuals in the room. So the multi-microphones allow you to steer the sensitivity point, but really software figures out what's in the room by looking at the 3D map.
Thank you.
Yeah, Dean Takahashi with VentureBeat. Microsoft's folks have talked about cloud processing advantages that they could get over time. Have you guys sort of architected this into the hardware in some way, or I mean, is that completely dependent on upgrades in data centers, I guess?
Well, I'm not really qualified to answer that aspect. I'll plead being the SoC hardware architect to that question, but certainly we consider the cloud and the things that we've done with live so far are an important aspect of the Xbox business today, and probably be a larger portion of it going forward.
And then can you just talk about the sort of advantages of starting out with an integrated graphics CPU chip this time instead of doing the two separate chips last time?
Oh well, they're tremendous. I mean I mean that being part of what I've been responsible for. I think that even having the large chip that we have is it's well worth having the large chip rather than having two separate ones. When you want to have an integrated system like we do, where the CPU and GPU can pass use of data back and forth and the other processors, I mean, having to have, no matter how good a link we had between them, there's no good place no perfect place to put a link like that. And so we have a more cost-effective, better performing system now to start with, and obviously it'll provide advantages as we make cost-reduced versions of it in the future.
Satoshi Matsushita, NEC. In terms of the cost, the manufacturing test has a significant impact on it. Have you had any specific? Do you have any special technique for that, reducing the manufacturing cost of the chip?
Well, there's nothing particularly unique or special. I mean, certainly nothing unique to this design that hasn't been done before. As I've been talking about the large on-die storage being repairable, it is also the case that some of the other processing logic is redundant as well, and so that provides provision for repair. But otherwise, it's relatively conventional in terms of how the chips are tested and manufactured.
We have time for one more question. Mark Harwin, Stanford University. And one of the things, I'm over here. One of the things that I've noticed in a lot of computing systems is that the sort of idle memory power is actually significant, both because of the active idle power in the DRAM channels, and as well as the leakage power of the on-chip SRAM. So I was wondering if you could just mention what is the sort of active idle power or the leakage power of the SRAMs and just the idle power of the DRAM channels? Right. So not the circuitry you did, but just the other stuff.
Well, I'm not going to mention specific numbers in terms of watts, but we do in the ultimate sleep modes. We do put the memory into just a standby refresh data retention mode in terms of main memory. In terms of the on-die storage, we do have the capability. We do change voltage and frequency, so then and we can put we turn off sections of the chip that we're not using completely.
Okay, thanks.
Good. Okay, thank you.
Thank you very much.
Let's thank our speaker. Thank you. So last but not least, we have Ramana Rachakunda from Intel. We'll talk about Clover Trail, Intel next Atom SoC smartphone platform. So Ramana is a chief SoC architect with Intel. He worked on several Atom SoCs in areas of power management, clocking, and interconnect architecture. Ramana also worked on power management and bus architecture on Atom CPUs. Prior to that, Ramana worked on Intel Pentium processor performance analysis and optimization. And before Intel, Ramana worked as cache controller and memory controller architect in a Spark system at ROS Technology. He has a master's in electrical engineering from Virginia Tech. Please welcome Ramana.
Thank you. Good morning. I'm going to talk about Intel's next generation smartphone SoC called Clover Trail. First, we're going to go over an overview of the SoC and the different components inside the SoC. We'll also look at the generational improvements from the first generation SoC called Medfield. And we'll dive into media, imaging, and power management improvements. And lastly, we're going to look at the power and performance of the Clover Trail Plus SoC. Clover Trail Plus is a dual-core Atom processor based SoC. And it also has a dual-core graphics processor. Sorry. And it also has a LPDDR2 memory controller and video decode and encode engines. It's built on a 32 nanometer high-K metal gate process. And sits inside a 14 by 14 CoPOP package and ISA compatible with Intel Core processors. Looking inside the Clover Trail Plus SoC block diagram, like we talked about, it's a dual core Atom SoC, Atom CPUs with 2 threads per CPU for a total of 1 megabyte of L2 cache and with frequency scaling support. The CPUs are connected to the memory controller using a NOT SoC interconnect. And the memory controller is a dual channel 32-bit memory controller running at 533 megahertz or 1066 megatransfers a second with support for 2 ranks per channel. This gives a total bandwidth of up to 8.2 gigabytes a second. We also have a 3D, 2D graphics processor engine, which is the SGX 544 MP2, running at up to 533 megahertz. Video decode and encode are hardware accelerated and support encode all common encode formats, including H.264, VC1, and MPEG-2. There's a image signal processor on the SoC that supports still image capture offload as well as video capture and offers a dual camera support. There's low power I/O support for SDIO 2.1 as well as MIPI HSI. There's a integrated security engine that offers features such as secure boot and crypto offload, similar to the ARM trust zone. There's also integrated audio DSP for low power audio applications. Audio decode, MP3 audio decode is offloaded into the audio subsystem without not much CPU requirement to run the decode on the CPU. And looking a little more deeper into generational improvements from the Medfield phone, which is the first generation phone from Intel. The Clover Trail Plus phone offers 2 Atom cores running at 2 gigahertz compared to the 1 core with 2 threads. The Clover Trail Plus phone has 2 cores and 4 threads running at 2 gigahertz. The memory is improved from 800 megatransfers per second LPDDR2 to 1066 megatransfers a second LPDDR2 to give additional bandwidth for the extra CPUs, as well as the dual core MP2 graphics engine. eMMC 4.3 on the Medfield phone supported up to 64 gigabytes. eMMC 4.41 now supports on the Clover Trail Plus phone up to 256 gigabytes. Like I said before, the graphics was a single core SGX 540 running at 400 megahertz on the Medfield phone. It's a SGX 544 MP2 running at 400 megahertz on Clover Trail Plus phone, but it has a capability to burst up to 533 megahertz. The first generation phone supported all the standard codecs for video decode. The Clover Trail Plus phone added support for VP8, Real Video, and Sorensen. The Clover Trail Plus phone supports a 13 megapixel rear camera, compared to the 8 megapixel, and a 2 megapixel front-facing camera compared to the 1.3 megapixel before. Display-wise, MIPI DSI on both of them, except the Clover Trail Plus phone supports 1 gigabits per second per lane, and as opposed to 700 megabits per second per lane. That improved the resolution support from 13:7 to 19:12. And the MIPI DSI is concurrent. You can actually display 2 different images on the MIPI panel and an external HDMI. The first generation phone supported all of the standard IOs, but we added an additional ULPI for an internal USB and additional PWM and I2Ss. Cellular modem support supported up to 21 megabits per second using the Intel XMM 6260. With the Clover Trail Plus phone, the support is up to 42 megabits per second using the Intel XMM 6360, I'm sorry, and the LTE modem support is coming soon. Clover Trail and Clover Trail Plus were designed together with same design teams. The Clover Trail was targeted more for Windows tablets, and Clover Trail Plus was targeted towards Android phones and Android tablets. And Clover Trail was slated for holiday refresh of this year, and Clover Trail Plus phones as well as tablets for Android was slightly after that. The real success drivers for the project were we started from a very solid first generation SoC baseline and only added features as required and reused more than 70% of the hardware and firmware as well as existing drivers. Intel was able to deliver both of these SoCs of the same base architecture with very minor differences. One of the differences is the SGX 544 MP2 versus the 545, which offers greater performance on the Clover Trail Plus, 4x the gigaflops, 3x the triangles per second, and 2x the pixels per second on demand burst. Clover Trail Plus also improves memory bandwidth and utilization. And there's also improvements in the fabric UART optimizations. The Medfield platform, like we talked about, had one core with 2 threads. And we went to 2 cores now with 4 threads. And this increases performance by adding additional logical CPUs on top of a physical core. The threading, with 4 threads, as far as the operating system is concerned, it looks like it has 4 cores, 4 logical processors. And the architectural state is replicated per thread. But each 2 cores inside the same, 2 threads inside the same core utilize the same processing hardware and share the same processing hardware. Simultaneous multi-threading offers efficiencies, including lower area for additional logical processor. As well as higher frequency at the same voltage. Simultaneous multi-threading interleaves the multiple threads within the same in the same pipeline on the same core. Superscalar in other architectures like the Atom cores will benefit the most from simultaneous multi-threading. And with simultaneous multi-threading, we support the switching the threads that's getting processed every cycle. And like I said before, for just adding 7 to 15% core area addition, excluding the L2, you get performance that's much greater than that. And we'll see some numbers later in the presentation. So looking at memory, media, graphics display, and audio improvements. The memory controller improved QoS algorithms and is able to handle multiple concurrent QoS streams to memory. And the memory controller also schedules out-of-order transactions out of order to DRAM for better performance. So the increased memory frequency, we talked about going from 800 MTS to 1066 MTS with the 2x32 LPDDR2. And that was primarily to feed the extra CPU and the dual-core graphics. On the graphics side, the GPU on-demand burst with CPU and GPU power sharing between the CPU and the GPU because of the power-constrained environment of the phones. Burst requests by graphics driver are made, and based on hardware activity monitors inside the GPU looks at the graphics driver looks at how active the GPU is, and based off of that requests a burst request. And I have another slide with more details later in the deck. The PM unit manages DVFS, and the energy management framework ensures optimal burst between the CPU and the GPU. As far as the display improvements we talked about before, the 19x12 MIPI DSi panel support and the 1080p 30 over HDMI that are capable of happening simultaneously. The wide-eye stack was optimized for lower latency. And in the clone mode, the end-to-end latency is around 60 to 80 milliseconds now for 1080p. And the audio engine for ultra-low power music playback, the MP3 decoding happens inside the audio engine, and the platform power is less than 65 milliwatts of platform power because the audio decoding is offloaded into the audio engine as opposed to being done on the CPU. Camera subsystem improvements. There's an image signal processor. The image signal processor gets the data, the image stream from the sensor module and through the CSI2 interface. And some of the improvements here include zero shutter lag, continuous viewfinder, time shift, and multi-threading kind of ability inside the image signal processor enables some of these features. High dynamic range HDR features were done primarily on the Atom CPU, and now they're offloaded onto the image signal processor. So power delivery, codec, and PHY disaggregation. On the Medfield platform, the charger, all of the power VRs, voltage regulators, the USB PHY, audio codec, and HDMI were inside a single PMIC. These were disaggregated for getting a cheaper PMIC, as well as giving flexibility for OEMs to select different PHYs as well as audio codecs, et cetera, and charger solutions. This ends up in a cheaper PMIC as well as greater flexibility for the OEMs. Power management, dynamic power management features like S0IX and D0IX. Let me quickly kind of go over this. And when the phone is off and I guess in your pocket, the phone is generally in an S3 state. When there's a user activity of some kind or an incoming phone call, we go into an S0 state, and the apps acquire a lock to prevent further entry into S3. Drivers for each subsystem, when they're done, take the subsystem into a D0IX state. And when all of the components are in a D0I3 state, the platform enters an S0I3 state. When wake, when all of the locks are released by the apps, the Android PM pushes the platform into an S3, back into an S3 states, where the OS timers are disabled. So here I have a die map with blocks superimposed to kind of show where the different components inside the SoC are. And we have the infrared die image kind of showing that both the CPUs are active, and you can kind of see the CPUs as well as the L2. That's the CPU active stage, we call S0. You can kind of see the graphics as well as other features. This kind of shows the CPU is idle, and you see a very small portion of the CPU on to just save some state. And we go into the SoC idle, which is the lowest power state for the SoC. And the SoC, you can kind of see only a small portion of the SoC is glowing. So I'm quickly running out of time, so I'm going to go quickly through the slide. Like we talked about before, this is the CPU-GPU power sharing. The graphics driver continuously monitors the GPU activity and requests when a certain threshold is crossed. The GPU driver requests for bursting from 400 megahertz to 533 megahertz. All the system control unit continuously monitors skin temperature and thermal state and computes thermal credits available. And based on that, the thermal and frequency manager decides whether or not there are enough thermal credits to go to a higher graphics frequency. If there are, the system control unit actually switches to the higher frequency. So let's look at performance compared to CPU performance compared to the prior generation Medfield SoCs. You can see that the single thread performance is about even on the AND-E bench, that primarily focuses on integer operations. And you can see the two-thread performance is slightly higher. That's because it's the Medfield platform is running on a single core with two threads versus the same on different cores on Clover Trail Plus SoC. And you can see the Clover Trail Plus improves performance over Medfield by up to 2x on the fourth thread. Graphics performance, you can see compared to the Medfield SoC platform is almost 3x the performance. But the phones nowadays are used more than for more and more for non-voice calls, including gaming, browsing, and social networking apps. And you can see the various apps that we kind of tend to use more than just voice. So what does it mean for user experience for a phone? We compared the user experience is really two things that we do primarily with the phones, which is web-based applications that use JavaScript and HTML5. So we compared it to two of the smartphones, ARM-based premium smartphones on the market today. And you can see on web-based applications that the Clover Plus phone provides a great user experience on browser-based usage scenarios. Web Expert, which contains photo effects and face detection and stock dashboard, as well as offline notes, are some of the components in that. Is something that is a stand-in for user experience, and we see Clover Trail Plus is doing pretty good here. Clover Trail Plus system also has great Android user experience for Android apps. Mobile Expert, which measures that, which includes face detection, photo effects, creating collages, creating slideshows, and encrypting content. You can see that it fares pretty well here, and Clover Trail Plus provides a great experience for typical end-user applications on Android devices. Okay, so that's to recap. I think we have a 2x CPU performance, 3x graphics performance, and do pretty good on the user experience compared to smartphones on the market today. Okay, I think I'm actually out of my time. I don't know if there's any questions.
Hello, Satoshi Matsushi. Do you have any power consumption or battery life-based comparison against ARM-based smartphone?
I don't have any on the deck as you saw today, but we're very comparable to ARM-based smartphones on that.
Thank you.
Jim McGregor, Tirius Research. Obviously, another power question. With the integration and the performance improvements, can you at least give us maybe some figures in terms of what the benefits were in terms of power consumption on the SoC or the system level?
Again, I think my answer is going to be the same. I think we're very comparable. I think the power numbers are available outside, and we can talk about that offline. But I don't have any concrete numbers here.
All right, thank you.
Okay, thank you. No more questions? Thank you. Your mic not on.
Okay, sorry. So we're gonna have a half an hour break, and during which you could check out the student presentations, and we're gonna meet again at 11:30 for the keynote. There are also some announcements.